Hello everyone, welcome to the Study Hacks Institute of GIS and Remote Sensing. Today I will discuss an important topic, mainly satellite remote sensing for agricultural application. How we can really use the satellite remote sensing for agricultural application. Today's session, I will try to explain everything. So I hope if you are interested to the agriculture precision, this is for you. So let's go one by one. I will explain all of those things, mainly all of satellite remote sensing for agricultural application. I will try to explain and how we can easily monitor the different types of agricultural precision. So let's go. So first of all, why use satellites for agricultural application? There are a lot of uses for satellite for agricultural application, such as timely, objective, local to global coverage. So using the satellite imagery, we can easily produce our all of crop or crop yield prediction, everything we can easily do using the remote sensing technique, as well as it also very important for observing areas that are inaccessible. Suppose some area you cannot access, then using the remote sensing or using the satellite technique, you can easily accessible this type of region, and then you can observe this area. What is the condition for their crop? What is the condition for their productivity rate? So all of things we can easily do using the satellite remote sensing application. We also do for the monitor the plant growth and estimate crop productivity using this remote sensing application, and assess soil moisture and irrigation requirement. It's also very important for that agricultural sector. Identify soil and crop characteristics and conditions, as well as better forecast the precipitation and crop diseases, and maximize crop yield while reducing the energy consumption. Avoid the waste of farming input such as water, fertilizer, and pesticide. So basically, this type of things is very useful for the agricultural application using the satellite or remote sensing technique. So further, I also try to explain all of application. Practically, I will show you that. So now application for agriculture and food security. So basically crop monitoring. So mainly phenology, crop area monitoring, crop type monitoring, crop condition, yield, irrigated landscape, flood, drought, frost, accurate and timely reporting of agricultural statistics. It's very important for the agriculture and food security. Crop monitoring we can easily do using the remote sensing and satellite technique. So further, I'll try to show you the practical example about that. And crop forecasting. So it's very important using the remote sensing technique. We can easily forecast the accurate of yield of shortfall in crop production and food supply per region and country. And market stability, lower uncertainty and increase the transparency of global food supply, then reduce the price volatility by anticipating market trend with the reduced uncertainty. And humanitarian aid, so monitor of the food security in high risks in region worldwide, early warning of famine, as well as enabling the timely mobilization of international response in food aid. So for this type of region, it's very important for that application of for agriculture and food security. So now biophysical characteristics derived from remote sensing applications such as chlorophyll content and above ground biomass, as well as leaf area index. So leaf area index is mainly one side green leaf area per unit ground area in broadleaf canopies and half of the total neat leaf surface area per unit ground area in the conifers canopies. And photosynthetic primary production is very important. So measure of how much carbon dioxide vegetation takes in during the photosynthetics minus how much carbon dioxide the plants release during the respiration. So it's very important about that photosynthetic primary production. We can also monitor using the remote sensing technique and also measure how much carbon dioxide vegetation takes during the photosynthetics. Okay, so we can easily do it. And then fraction of the absorbed photosynthetical active radiation. So basically it is the represent the ratio of the solar radiation that is absorbed by the vegetation for photosynthesis, used for assessing the impact of growth on vegetation. So now talk about that satellites and sensor for agricultural application. So basically here you can see this is the list about that. So this type of satellite and this type of sensor we are used in the agricultural application. And here you can see some product: land surface reflectance, evapotranspiration, land surface temperature, precipitation, soil moisture, vegetation greenness, structure. So this type of product we can easily monitor using this type of satellite and their sensor. So here you can see this type of satellite. I will explain all of those things one by one, such as Terra, Aqua, Suomi, NPP, NO, AA20, Landsat 8, Sentinel-2, Landsat 8 and Sentinel-2. Okay, so International Space Station, Land Data Assimilation System, Global Precipitation Measurement, CHARPS data set, Soil Moisture Active Passive, Sentinel-1. So all of you can see also that sensor about that. So basically you can get the Terra for the MODIS, Aqua for the MODIS. So we can see VIR sensor. So all of those things I will try to explain. And also you can see for the Terra, this you cannot do for that. This type of sensor you cannot capable for doing the land surface reflectance. Okay, also you can see the evapotranspiration. So further let's try to discuss all of these things one by one. So first of all, land surface reflectance. So land surface reflectance, it's provide an estimate of surface spectral reflectance as measured at the ground level by accounting for atmospheric effect like aerosol scattering and thin cloud, and useful for measuring the greenness of vegetation, which can then be used to determine the phenological transition dates, including the short of season, peak of period, as well as also end of season. Okay, and then input for generation of several land product vegetation indices, biodirectional reflectance, as well as distribution of the function and thermal anomaly, snow ice, and fraction of absorbed photosynthetical active radiation, and the leaf area index. Now we talk about that satellites and sensor for land surface reflectance for MODIS. So MODIS is the cross satellite, and the full form of the MODIS is the Moderate Resolution Imaging Spectroradiometer, MODIS. And MODIS instrument on two NASA platform. One is the CRA. So basically it will be 1992 to the present time. Another is the Aqua. It will be start from 2002 and to the present time is available for the CRA and Aqua. These are two platform. And the special resolution is the 250 meter. We can get that 500 meter as well as 1 kilometer. So this is the special resolution about the MODIS, CRA and Aqua for that land surface reflectance. And spectral resolution, mainly we can get the 36 bands ranging in the wavelength from 0.4 micrometer to 14.4 micrometer. And temporal resolution, we can get the dataset for daily, 8-day, 16-day, monthly, as well as we also get the data for yearly. And this dataset is available from 2000 to present time. 2000 to present time, we can get this data. And further global coverage with the orbital gaps in the tropics. So here you can see some MODIS data, also their product name, also their special resolution, and also their temporal resolution. So here you can see about that. One is the surface reflectance. So this surface reflectance, we find out it's a short name. Okay, so mod 09 is a short name. And we find out the temporal resolution. You can see 250 meter and 500 meter. And temporal resolution, find out that daily and 8-day. Land surface temperature, you can see about that. Its name is the mod 11. We find out that 1000 meter daily and 8-day we can get it. Land cover changes, we can get the 500 meter. 8-day and yearly you can get it. Then vegetation indices, we can see we can get the 250 meter, 500 meter, 1000 meter. Also we can see about that. Thermal anomalies. So you can see that a lot of product is available for the MODIS, and also their resolution and their temporal resolution. So it's very important for agriculture monitoring using the satellite MODIS. So now we talk about that how we can easily satellite and sensor for land surface reflectance. It's called the VIIRS. So Visible Infrared Imaging Radiometer Suite. So this is the full form of VIIRS. So basically this has two platforms. One is that we can get the Xiaomi National Polar Orbiting Partnership and NOAA 20. So this is the two platform you find out. And this special resolution is the 375 meter to 750 meter. And spectral resolution is the 22 band. We find out from here. And then temporal resolution, we find out the daily, 8-day, 16-day, monthly, and yearly data set is available for that. And it's available from 2012 to present time. And it's global coverage. We can easily get the data for globally. So now we talk about that satellite and sensor for land surface reflectance, mainly OLI. So OLI, mainly it's the Landsat dataset. So basically Landsat 8 launched on February 11, 2013. And this instrument is that OLI. So this full form is the Operational Land Imager. OLI, Operational Land Imager. And we find out that another is the thermal infrared sensor. So OLI and TIRS, mainly Operational Land Imager and Thermal Infrared Sensor. These two sensors mainly useful for Landsat imagery. And the Landsat data have been produced, archived, and distributed by the US Geological Survey, USGS short name, since 1972. And builds on 50 years of the Landsat program, offering the longest continuous global record of the Earth's surface. So OLI, these things is that Operational Land Imager for Landsat 8. This special resolution is a 30 meter. And spectral resolution mainly find out that 9 bands ranging the wavelength from 430 nanometer to 2290 nanometer. And temporal resolution for OLI, Landsat 8, we find out that 16 days. And it's available from 2013 to present time. And it's the global coverage. We can easily get the data set for the globally. And now we talk about that another instrument. It's called the multispectral instrument. So basically MSI. So basically it provides for Sentinel-2A and Sentinel-2B. So basically Sentinel-2A launched on June 23, 2015, and Sentinel-2B launched on 17 March 2017. And we can get the constellation of two polar orbiting satellites in the same sun synchronous orbit, based at 180 degrees to each other. And collaboration between the European Commission and European Space Agency and European Union. It's the collaborate. And sensor name is the multispectral instrument. So now we talk about the multispectral instrument. So basically, this special resolution is the 10 meter for VNIR, 20 meter for radius and short wave infrared band, and 60 meter for atmospheric bands. And spectral resolution is the 13 bands from VNIR to short wave infrared 1 band in wavelength from 0.44 micrometer to 2.2 micrometer. And temporal resolution for the multispectral instrument is the 5 days. So it will be available from year of 2015 to present time. And level 2A product provide the orthosified bottom of the atmosphere, mainly BOA reflectance. And it's also global coverage. So now we talk about that HLS. So basically it's the harmonized Landsat and Sentinel-2. So HLS, it's mainly useful for combining the land surface observation of OLI and MSI, okay, into a single dataset, and it observation at 30 meter resolution every 2 to 3 days, okay, and gridded to a common pixel resolution map, projection, and tile, and atmospherically corrected and cloud marks. So that's why you can get the very clear imagery when I use it, and normalized to a common nadir view geometry FI VRDF estimation. So now we talk about the evapotranspiration. So it's very important for the agricultural sector. So sum of evaporation from the land surface plus transpiration in vegetation, and highly variable in space and time, it will be changed region to region or space to space, it will be changed. And critical component of the water and energy balance of the climate soil vegetation interaction, and extremely useful in monitoring and assessing the water availability, drought condition, and crop production. So this is very important factor for evapotranspiration. Using that, we can easily assessing the water availability, drought condition, and crop production. So further, I also try to show you all of practical example. And remote sensing has long been recognized as the most feasible means to provide the especially distributed regional evapotranspiration information over the land surface, and cannot be measured directly with satellite instrument, and model output are the depend on many variables such as land surface temperature, air temperature, solar radiation, humidity, albedo, soil condition, and vegetation cover. Satellites and sensor for evapotranspiration MODIS. We can also monitor the evapotranspiration using the MODIS. So for that, MODIS mod 16. So basically this mod 16 level 4 evapotranspiration and latent heat flux, it provides 8-day interval, or also put the yearly interval, you can get it from this data set. And especially resolution is the 500 meter for that. And we can get the data set from year of 2001 to present time. And it also global coverage. So now you talk about that eco-stress, how we can easily use the eco-stress to monitor the evapotranspiration. So basically, eco-stress is that ecosystem space-borne thermal radiometer experiment on space station. The short form is the eco-stress. So eco-stress instrument mounted at the International Space Station, or ISS, and measure the agriculture water consumption over the continental US at the special temporal scale for drought estimation, and covers mainly CONUS, key biomass, agricultural zone, selected FluxNet sites, etc. And eco-stress, basically, this is a full form, ecosystem spaceborne thermal radiometer experiment on space station. Basically, it's available from year of 2018 to 9 July 2018 to present time, and spatial resolution is 70 meter. Okay, and this is the spectral resolution 8 to 12.5 micrometer, and thermal resolution mainly variable depending on the ISS. So now we talk about that LDAS. LDAS mainly land data assimilation system. How we can easily use the land data assimilation system and monitor the evapotranspiration. So basically, it's provide the model-based ET data, of which there is a global collection and North American collection. So GLDAS, it's mainly global collection, and NLDAS, it's mainly North America collection. Integrate the satellite and ground observation within the sophisticated numerical model based on water and energy balance method. Especially we find out the 0.25 degree to and 1 degree. And thermal resolution will find out the 3 hourly, and then daily, monthly, it will be present from 1948 to present time. Now land surface temperature. So basically land surface temperature product show the temperature of the land surface in Kelvin, but we can easily convert into degrees Celsius also. And different from the air temperature measure, at it provide the temperature of the whatever is on the surface of the earth, such as bare sand, ice, snow, covered area, leaf covered tree canopy, roads, etc. And then useful for monitoring the change in the weather and climate pattern, and used in agriculture and water resource management to allow the farmers and decision makers to evaluate water requirement. It's very important for agricultural sector. And then we talk about that MODIS, how we can easily use the MODIS to monitor the land surface temperature. Basically, MODIS Mod 11 is the land surface temperature and emissivity level 3 product, available from both TRA and EQUA satellite is available. And temporal resolution mainly we find out the daily, 8-day or monthly. Especially resolution 1 kilometer, 6 kilometer, and 0.005 degrees, we can get it. It's available from 2000 to present time. And it's the global coverage, and this is the short product name, Mod 11, for that land surface temperature from MODIS. So now we talk about that, how we can easily monitor the land surface temperature using the VIIRS. So basically it's the visible infrared imaging radiometer suite. So this is the land surface and emissivity level 3 product for that, and temporal resolution daily or 8-day, and spatial resolution 750 meter and 1 kilometer. It will be available from 2012 to present time, and global coverage. And this is a short form about that, mod 16A2. So now precipitation. So precipitation is a key component of the water cycle and difficult to measure since rain and snow vary greatly in the both space and time. So satellite provide the frequent and accurate observation and measurement of rain and snow around the planet, especially where ground-based data are sparse. Radar or radiometer estimate the measure the intensity and variability of latent heating structure and precipitation system. Agricultural community needs to know the timing and amount of rain or snow to forecast the crop yield, as well as also freshwater shortage affecting the irrigation and the production. So now we talk about that how we can easily monitor the precipitation using GPM. GPM mainly Global Precipitation Measurement Mission. So joint mission between NASA and JASA, and integrate the multi-satellite retrievals for global precipitation measurement product. And this is the 0.1 into 0.1 grid, okay, 60 degrees south to 60 degrees north, and it's available from 2000 to present time. And it's the level 3 product for half hourly, daily, or monthly data set is available for the GPM. And now we talk about the CHARPS satellite imagery for precipitation. So basically the full form about the CHARPS, it's the Climate Hazard Group Infrared Precipitation with the station data, and rainfall estimate from rain gauge and also satellite observation, and developed by the Climate Hazard Center in mainly California, UC Santa Barbara, and incorporate in-house climatology. We can get the resolution 0.05 resolution infrared satellite data, as well as it's available from the 1981 to near present time. It's available. So now we talk about that soil moisture, basically SMAP, soil moisture active passive. So this is a full form about the SMAP. And then L-band passive radiometer receive the energy in narrow microband 1.41 gigahertz. And level 4 product assimilate the SMAP L-band brightness temperature data into a land surface model generating to root zone and surface soil moisture. And spatial resolution mainly 9 kilometer about the dataset. Temporal resolution 3 hourly and daily is available for that. So now you talk about that L-DAS mainly land data assimilation system, how can they use to monitor the soil moisture. So use numerical model to integrate the satellite information with the ground-based data and output estimate of the soil moisture, temperature, and evapotranspiration. So now we talk about that satellite and sensor for the vegetation greenness. So healthy vegetation absorb the blue and red light to fuel photosynthetic and also create the chlorophyll. A plant with a more chlorophyll will reflect more near infrared energy than an unhealthy plant. Thus, analyzing a plant spectrum of both absorption and reflection in visible and near infrared wavelength can provide the information about the plant's health and productivity. Reflected near infrared radiation can be sensed by satellite, allowing the scientists to study the vegetation from space. So now NDVI, so it's one kind of, you can see, normalized difference vegetation index, and based on the relationship between the red and near infrared wavelength, basically advantage is for that efficient and simple index to identify visited area and their condition, reduce sun angle, shadow, and topographic variation effect, enable large-scale vegetation monitoring, allowing comparison of different regions through the time. So NDVI, basically this is the formula about that, near infrared minus red, near infrared plus red. So here you can see about the example about NDVI being calculated from healthy green vegetation. Sensing the vegetation, you can see about that. So here you can see about that it near infrared, you can get the 50% and it 8%. So further we can find out that we can get the 0.7. So it's identify about the healthy vegetation and it can show about the 0.14. It's identify about that not much healthy vegetation. So now NDVI application, there are a lot of applications such as for NDVI, such as phenology, then road indicator, then vegetation health, then carbon monitoring, then leaf area index. So all of those things that are a lot of use for NDVI. So now we talk about that for vegetation monitoring using the MODIS. So basically MODIS Mod 13 is level 3 product for vegetation indices. Two primary vegetation layers retrieved from the daily and atmospheric corrected and biodirectional surface reflectance. One is the NDVI, another is the EVI. And a special resolution, we find out the 250 meter, 500 meter, and 1 kilometer. And temporal resolution is available for 8 day, 16 day, monthly. It's available from 2000 to present time. Now we talk about that visible infrared imaging radiometer suite, how we can use to monitor the vegetation greenness. Basically, it's the level 3 product, PNP. And now provide the vegetation indices by the process of selecting the best available pixel over a 16-day and monthly acquisition period. Three primary vegetation layers it provides: NDVI, EVI, and EVI2. We can get it from here. And a special resolution 500 meter, 1 kilometer, and 0.005 degrees. And temporal resolution will be 16-day monthly, and it's available from 2012 to present time. So now we talk about the OLI. So basically, operational land imager. This is the it also useful to reflect the drive the NDVI are produced on the demand from USGS. It can also be calculated using QGIS. You can also do it, as well as Google Earth Engine or other types of things you can also use. So spatial resolution 30 meter, temporal resolution 16 days, and 2013 to present time. And it's covered the global. So now we talk about the MSI, basically multi-spectral instrument. So it's available for the Sentinel-2. Reflectance drift from NDVI can calculate it using QGIS, Synap, or Google Earth Engine. And then spatial resolution is 10 meter, temporal resolution 5 days. It's available from 2015 to present time. And it also global coverage. So now we talk about the SAR data. So basically SAR is the synthetic aperture radar. This is the advantage of that and also disadvantage about the SAR. So basically advantage is the nearly all weather capability. Suppose using the SAR data, your region is very cloudy, then you can easily get all of information. Okay, so it's totally provide you with a very clear and neat and clean imagery when you use the SAR data. Nearly all weather capability. Okay, day or night capability. We can get the image for day or night using the SAR data. Penetration through the vegetation canopy and penetration through the soil, minimal atmospheric effect, sensitivity to dielectric properties, liquid or frozen water, sensitive to structure. And disadvantage is that information content is different than optical, sometimes difficult to interpret. And statistical effect, mainly it's the graininess in the imagery, effect of topography. We can get some shadow or other things about that. Land cover mapping, optical versus radar. So basically in the optical, energy reflected by the vegetation is dependent on the leaf structure, pigmentation, and moisture. On the other hand, microwave energy is scattered by the vegetation, depend on the structure, size, density, or orientation, and dielectric properties of the target. Optical, mainly its products are available from visible to infrared wavelength and consisting of the several bands of data. But radar singles are typically only at a single wavelength of each sensor. Optical sensor only see surface tops because the canopy blocks the understory, limiting the increase of the land cover and land use to only when these are correlated well with this characteristic at top layer. And the single can penetrate through the canopy and providing the information on the soil condition and inundation state. So now penetration, basically it's one kind of function of wavelength, is the primary factor in the wavelength selection. Generally, the longer wavelength, the greater the penetration into the target. Such as here you can see about that, this type of penetration, this type of band, X band, C band, L band, 3 centimeter, 5 centimeter, and 23 centimeter. and also there use the frequency band. We can get the application, for example. So here you can see, basically you can see about the L band. It's also useful for the agriculture, forestry, or soil moisture. Also X band, you can see agriculture, ocean, high resolution, radar. So you can see this type of frequency band and this type of application for there is frequency band we also use. And P band, here you can see biomass, soil moisture, penetration. Okay. So there are this type of use for the different types of frequency band. And now Sentinel-1. So Sentinel-1 is mission for that. This is the link about the and constellation of the two polar orbiting satellite. We can get the C band. So basically C band, here you can see basically C band is used for the ocean and agriculture. So that's why the SAR data, there are a lot of uses in the agricultural sector. So C band, synthetic aperture radar, and temporal resolution 12 days, and we can get the dual polarization VB plus VS or SS plus HB. 2014 to present time it's available. So now limitation of satellite data. Okay. So first of all, it's difficult to obtain the high spectral, spatial, and temporal resolution with the same instrument. Then optical sensor cannot penetrate cloud or vegetation cover, which can be lead to data gaps or a decrease in the data utility. Spatial resolution, while across the resolution data provide a synoptic view, the spatial resolution is too coarse for field level assessment. Temporal resolution, mainly many satellites only pass over the same spot on Earth every 3 to 5 days, and sometimes as seldom every 16 plus days. Spectral resolution, basically multispectral instrument observe the reflected and emitted light in the broad wavelength lengths for the particular band with a limited number of bands. And large amounts of data exist in a various file format, file size, and from multiple sources. And knowledge of data and tools is required to work with satellite data. So basically, this is the things I will try to explain about that, how we can really use the remote sensing in agricultural sector. This is the theory part, but further I also try to explain about all of practical part, how we can really use this type of things and practically we can do it. Okay. So today is no more. So further session, I also try to explain a lot of things about that, how we can really use the satellite remote sensing for agriculture application. Then I hope you can really learn a lot of new things. In the meantime, if you want to join my online training program for GIS or remote sensing learning purpose, you can simply contact in my WhatsApp or email. You can get all of information in the video description. Further, if you are interested to learn the Google Earth Engine or GIS remote sensing or any other application for satellite or GIS, then you can simply contact. And further, you can either join my live training program. Today is no more. Thank you for watching that. Stay happy, stay safe.